It has been quite some time now since play developed in starboard outdrive. With every trip out into the ocean, the situation is gradually getting worse and worse. It's exactly like driving a car. If the tie rods are loose, you have to constantly make steering adjustments, just to drive straight. And that is precisely the situation with my boat. I have to keep turning the helm all the time, continuously correcting my course, to move it in a straight line. Also the waves constantly knocked us off course, making steering the boat even more difficult. Also the autopilot handled the task quite well, and unlike me didn't complain. I know exactly what the problem is, and precisely what needs to be replaced. I have already bought all the necessary parts, so I can get started on the next repair. As always, the job turned out to be far from simple. I had to improvise and use my wits. But now I'll show you in detail exactly how I did everything and what the final result looks like. Ultimately, everything worked out perfectly, with absolute minimum of time and money spent. Disassembling the outdrive has become routine for me. I have taken it apart so many times that I no longer even consult the repair manual. Nevertheless, I'll still include screenshots from the manual here to ensure complete clarity and visual guidance for those who may never have disassembled an outdrive before. Moreover, many people dislike my poor English and find it difficult to understand and follow. You can watch the video with the sound off, and it'll be still clear exactly what I am doing and how I am doing it. I think this will be interesting to anyone planning to do similar repair of their boat. Meanwhile, I am already disassembling the trim cylinders. To do this, I pull out the cotter pins and remove the pivot pins. I won't completely disconnect and remove the cylinders. That isn't necessary right now. Now the clamp on the exhaust bellows have to be loosened. Without the clamp, the exhaust bellows can be removed easily, even if it hasn't been removed in 10 years. Next, I loosen the clamp on the water inlet hose. To detach the U-joint bellows, fold the lower edge of the bellows inward. It will then easily disengage from the lip of pivot housing. I tightened these bolts with Loctite last time, so it takes some effort to unscrew them. Next, I unscrew the tilt sender. Here I am screwing the ground terminal. I apologize that you can't see anything. My nape is blocking the view. To access the steering shaft, I have to remove the entire gimbal ring and pivot housing assembly, preferably without damaging any surroundings. The gimbal ring has dislodged from its seats. Now the lower pivot pin needs to be extracted. To do this, I pull out the cotter pin and try every possible way to extract the pivot pin. I finally managed to get it out. It's heavily corroded, so I am going to replace it. I'll put in a new one. Now, to free the shift cable, I unscrew its retainer. Nothing else is in the way. I can now remove the gimbal ring with the pivot housing. I don't disconnect the cylinders, they just stay hanging there. They won't get in the way of anything. Here is my main problem, but not the only one. This is what it looks like from outside the boat and from inside. I am unscrewed the bolt and gonna try to extract the steering shaft somehow. Though I am not sure exactly how just yet. According to the manual, the procedure requires first removing the engine, then the transom shield. Only after that can the steering arm be removed, and only then it is possible to extract the steering shaft. I am not quite ready for that volume of work just yet. I would prefer something simpler and quicker. Unexpectedly, the steering shaft slid out on its own, without any effort, and without the need to remove the engine. The shaft mounting faces are no longer square. They have become severely rounded. Now it's clear where such excessive play came from. Significant play was also discovered in the pivot pins of the pivot housing. This requires replacing the pivot pins, the bushings and the pivot housing itself. But all of that can wait. Right now I have to replace the steering shaft. I am trying to pull the bushing down, out from the bolt, even though, according to the manual, it should be pressed up, into the bolt. However, doing it the proper way would require removing the engine and the transom shield, something I have absolutely no desire to do. Using improvised tools and homemade pullers, I still managed to pull out the bushing for replacement. I have to check how the steering shaft fits into the steering arm. Otherwise, the mounting in the steering arm might also be worn out, and it would have to be replaced too. It's not possible to simply insert the steering shaft into the steering arm. To do this, I must first screw a stud into the nut located above the steering arm. Then, while holding the steering arm in place with the stud, insert and press fit the steering shaft into it. Although the play is currently minimal, the steering shaft slides into the mounting seat far too easily. Given such a loose fit, and even with minimal play, the mounting seat will begin to wear out from day one. This is completely unacceptable to me. I have two options. The first is to remove the engine along with the transom shield and replace the steering arm. But what if that doesn't help? What if there is no wear there? After all, the steering arm is steel, while the steering shaft is aluminum. It's highly unlikely that the steel part has worn down to the same extent as the aluminum one. Moreover, the new steering shaft looks somewhat suspicious. In terms of quality, it doesn't resemble an original Volvo Penta factory part, despite having been purchased from an authorized dealer. I chose the second option, to apply a coating to the seating surface. That is, to increase the dimension of the seating area. Just to be sure, I asked Google AI what metals this shaft was made of. It confidently replied that it was stainless steel. Naturally, I didn't believe it. It looked far too much like an aluminum alloy. So I asked ChatGPT the exact same thing, and it too confidently stated that it was stainless steel, citing Volvo Penta technical specifications. Alright, let it be stainless steel. Who am I to argue with those two giants? In that case, I'll coat it with chrome or nickel or mixture of the two. Both metals are highly durable and resistant to corrosion in seawater. I just need to increase the dimensions ever so slightly. Around 10 microns should be quite enough to eliminate the gap. I have prepared everything for electroplating. I dissolved nichrome wire in the electrolyte using an electrolyte method. Purchased exit, alkali and distilled water, and mixed up a solution of water and baking soda. I already have a DC power supply. To begin with, of course, I need to experiment on other stainless steel parts in order to determine the optimal current strength and plating duration. To conduct the test, I took 304 grade stainless steel screw and 316 grade bolt, and strictly adhering the principles of electroplating, proceeded with the experiment. The odor generated during the process is extremely accurate, so I have to wear a respirator, even with the exhaust system running. It's not a quick process, but it seems everything is falling into place nicely. The screw has successfully acquired a coating, whether of chrome or nickel, though exactly what it is doesn't really matter. The main thing is the coating is there. Now I'll try to coat the bolt in the same way. The bolt turned out well too. Now I can try applying the coating to an old steering shaft to determine the optimal amount of time. The first time I keep the bolt and screw in the bath for 15 minutes. The second time for 30. The coating comes out black, but it polished beautiful to a mirror finish. Here are the results of the first and second trials. I proceeded to degrease the shaft in the alkaline solution, and that was when I got a surprise. A vigorous reaction began on the surface of the shaft. Aluminum only can react to alkaline in this manner. So this is indeed an aluminum alloy, and for aluminum the optimal surface treatment method is anodizing. Nevertheless, since I have everything ready for chrome plating, I'll try to apply a chrome coating to the aluminum, even though I know for a fact that it won't work, as an intermediate layer of copper is required between the aluminum and the chrome. For best results, the electrolyte should be heated. The copper tube acquires a high-quality chrome coating instantly, unlike aluminum. The resulting coating is uneven. I don't like it. I am gonna to anodize the shaft. It will be much better. The anodizing process differs completely from chrome plating. However, it utilizes the very same chemical substances: sulfuric acid, alkali, distilled water and baking soda. I am preparing the electrolyte using battery acid. It must be diluted with the equal amount of distilled water. Although the sulfuric mixture is no longer pure sulfuric acid, caution is still required when handling it. The acid should be poured into the water, and under no circumstances the other way around. Otherwise, the acid may boil and splatter in all directions. One serving isn't enough, so I am preparing a second batch of electrolyte. I degrease the shaft in 10% alkali solution, rinse it with distilled water and immerse it in electrolyte bath. The shaft will serve as an anode, to which I connect the positive terminal. A ring made of 304 grade stainless steel will serve as a cathode. I connect the negative terminal to it and adjust the current to 1 ampere. Anodizing is best performed with cooling, as this results in a more durable anodic film on the aluminum surface. To do this, I surround the electrolytic bath with ice. I gradually increase the current to 2 amperes, while carefully monitoring to ensure that the shaft doesn't overheat due to the high current. Otherwise, the coating will not achieve the desired hardness. More than an hour has passed, and the result is excellent. The oxide film is uniform and feels quite thick to the touch. An hour and a half has passed. I think that will be enough. The result exceeds all my expectations. I ended up with a perfect and a very hard surface. The marker leaves a trace on the surface that doesn't rub off during polishing. This indicates the dye is absorbed into the oxide layer. It turns out that my cooling was insufficient, and the oxide layer could have been made even more durable. I should lower the process temperature a little. It's a pity I don't live in Alaska. Now I also have to try anodizing the mounting surfaces for the gimbal ring. There is no need to increase the dimensions here. I simply have to protect the exposed aluminum from seawater. So I will try to limit the process to just 30 minutes. Inside there is a steel thread. Had it come into contact with the electrolyte, the anodizing reaction wouldn't have occurred. Therefore, I insulated the steel thread with silicone to prevent it from reacting instead of the aluminum. It looks great. 30 minutes is plenty. For anodizing, I'll be using this old stainless steel mud pan. Since I have to lower the anodizing temperature, I pre-freeze the entire prepared electrolyte. I can only cool distilled water, but not freeze it. And that is how I prepared the anodizing bath. I hope this amount of ice will be sufficient to maintain a reduced temperature throughout the entire process of anodizing my steering shaft. First of all, I clean all surfaces with acetone. Chilled distilled water for rinsing the shaft to remove alkali. And a frozen alkali solution that I prepared from a drain cleaner. Now I am filling the frozen bath with the frozen electrolyte, which I prepared from battery acid by mixing it in equal parts with the distilled water. I theoretically calculated the required volume and prepared slightly more. I hope this will be enough. Such a volume of acid emits a highly caustic odor. I must immediately put on a respirator. Well then, let's start by degreasing the shaft in the alkaline solution. To avoid losing precious microns in dimensions, I leave the shaft in the alkaline for just a few minutes. During the aluminum etching process, a residue forms on the surface. It can interfere with anodizing, so I simply brush it off in distilled water. I set the current to 0.5 ampere and begin anodizing. In that setup, the shaft serves as the anode, that is the positive terminal, while the stainless steel pan acts as the cathode, or the negative terminal. I constantly stir the solution. The bubbles indicate that the reaction is proceeding actively. The reaction proceeds stably, and the shaft doesn't overheat. The current can be increased to 1 ampere. Sometimes I take out the shaft and check it. So far, everything is going perfectly. I am increasing the current to 2 amps. My frozen solution has started to melt gradually. An hour has passed. For the bushings location, this is sufficient. Now the square mounting seat for the steering arm must be allowed to anodizing for additional 30 minutes. Here is the excellent result I got. Now I am doing exactly the same thing with the mounting surfaces for the gimbal ring. First the alkali, then distilled water, and finally I immerse it in the electrolyte bath. I sealed the internal steel threads with the sealant, apparently without success, as the anodizing process failed to initiate. I had to reposition the shaft, so that the electrolyte wouldn't come into contact with the internal steel threads. With this arrangement, the reaction proceeded normally. "30 minutes have passed. I think that's enough. I take it out, rinse it with water and baking soda, and assess the result. The result is excellent. I like it. There is just one last spot left to anodize. Anodizing the entire shaft will take nearly the whole day. I am screwing in a bolt because everything is anodized, so there is nothing to connect to. Another 30 minutes passed. I take it out, rinse it with water and baking soda, and see what the final result is. And the result is simply magnificent. Here the colors clearly demonstrate how the thickness of the anodization depends on time, and of course on the current density. But that isn't all. The shaft must also be boiled, so that the pores on the surface of this layer close up, and the coating becomes even more durable. I boil it in distilled water for 15 minutes in a pot that my wife allowed me to use. This is the before and after result. I polished the area for the bushing. The coating is much harder than aluminum and polishes very well. I am starting the assembly. First, I need to install the new bushing. And be sure not to mix up the top and bottom of the bushing. They are different. Since I don't have that special tool, I'll improvise with what I have. First, I pressed the bushing in flush with the edges. Then I had to seat it even deeper using the same washer that I had used to extract it. The proper installation depth for the bushing is unknown. The dimensions of 3.3 mm is specified from the top, but that location accessible only by removing the engine and the transom shield. However, through simple measurements and calculations, I determined that the actual depth is 4.5 mm. I am using my universal stud again. It has become the main special tool for this repair. I ordered brown rings, but they sent green ones instead. I hope it's the same FKM material, and the different color won't have any impact on its quality. Also, better you should go for the 65 by 5 size, not the 67 by 5 that I bought. To press the shaft into place without damaging it, I insert several plastic washers under the nut. Otherwise, water could seep inside through the bolts or ring. The shaft slides in with just a slight amount of resistance. I feel the size turned out perfectly, though I am not sure exactly how much I added. 8, 10 or 12 microns. At the time, my thinking was that if the shaft turned out too large and wouldn't press in, I could always polish off the excess and fit it to the dimensions of the tiller arm. It's done perfectly. No slack, no play. Now I have to replace the stud with a bolt. I had to remove the bellows, otherwise the stud couldn't be pulled out. I installed the new O-ring onto the bolt and tightened the bolt. I apply sealant to the mounting surface and put the bellows back in place. I am installing the gimbal ring and pivot housing. The bolts have to be coated with Loctite to prevent them from loosening due to vibration. I should have installed the plastic washer right away, but I forgot about it. Now I'll have to try to position it precisely in place by feel. I carefully drive in the new pivot pin and secure it with the cotter pin. I am applying sealant again, just to be safe, so that the water can't seep inside anywhere. I tuck the lower edge of the bellows inward, and it slides easily into the housing and locks into place. All clamps must be grounded, otherwise their lifespan will be short due to the seawater. I tighten the clamp on the inlet hose and fit the exhaust bellows onto its port. The bellows seated well and snugly all around. I can now tighten the clamp. I am tightening the ground terminal. All stainless steel bolts, threaded into aluminum, were pre-coated with Tef gel to prevent galvanic corrosion. Next, I install the tilt sensor. Next, the cylinders. Now the oil quality sensor wire. Now the shift cable needs to be put back in place. I have installed the cable and now securing it with the anchor. I nearly forgot to put the cotter pins on the cylinders, but it's not too late, even now. I've organized all the wires, tubes and hoses, and now I am trimming off the excess ends of the plastic zip ties. Now I am inserting the pitot sensor connector. Now new gasket. Before installing the outdrive, I apply sealant to both surfaces. Under no circumstances must water get in here. Lubricant renewing is also a necessary procedure. I insert the splinet shaft into the bearing and smoothly roll the outdrive into place, taking care not to damage anything nearby around. Pay attention to the shift cable. It must engage with its designated hole. The outdrive is now in place, so it's time to tighten the nuts. For the nuts, I am using the same TEF gel to prevent galvanic corrosion. You don't need to be a genius to tighten the nuts correctly. Everything is written in the instruction. The main thing is to precisely maintain the tightening torque of 68 Newton meters. Now I connect the shift cable. I do everything exactly as the instruction require. I tighten the cube 23.5 turns, the exact same amount as before the disassembly. Old cotter pin broke, so I'm gonna to replace it and put in a new one. Next, I have to connect the oil quality sensor. To install the cylinders, I need to remove the trolley. It's no longer needed here. Once again, I am using TEF gel in areas where stainless steel is in contact with aluminum and submerged. I installed trim pins and secured them with cotter pins. I install the plastic cover and fasten it with 6 bolts. I am refreshing the lubricant on the shafts, and now there is just one thing left: installing the propellers. With that, the repair will be complete, and I can head out fishing.